going to do the wave model of light for this one. And the wave model of light, we had hints of it the last time. When do we need to take into account the waves? When can we use rays of light? And what we saw was that last equation for single slits, as the slit gets smaller, the width gets bigger. And normally we just think of light going straight. But, you know, if this slit is really big, light's going to go. This is a black light, right? I'm joking, that's UV, that's not real, there's no thing as black light. It could be absence maybe or something, but it'd be interesting if the absence diffracts. Should. But as it would go through here, in general, we would think we would just have it come out like that. Okay? But when does this get so small that when it comes out, it starts going out like this and spreading light out? When does that occur? And where's that kind of cutoff? Is there a cutoff, hard cutoff, or is it soft going in a regime from one to another, where the ray model works and the wave starts to work? Or is there a place where both of them kind of work? Well, the answer is kind of at the end. Now, what the book does, they go through a little bit of analysis, and they use more circular openings, which is, I didn't do a circular aperture because circular apertures, you can just take a double slit, a rectangular slit, and rotate it 180 degrees. It's the same thing, basically. But what I want to say is they derive a little equation. They basically say that when the width or the diameter of that slit is equal to the square root 2 lambda L, and L again is the length from the view screen to the opening, the slit, the gap, the circular aperture, whatever you want to call it. At this point, this is kind of like a crossover point between rays and waves. Light acts as a ray when this D value gets when the width is kind of bigger than that, but when it gets smaller than that, then we start seeing more diffraction effects. So what the book does, they say for lambda equals 500 nanometers, which is kind of a reddish blue, green, something like reddish. That's not red, that would be more of a greenish blue. Around 500 nanometers and a view screen of about 1 meter away, they get that the size of this gap is about 1 millimeter. I'll put approximately here. Now, if you notice 1 millimeter compared to 500 nanometers, if you do the math for that, this gap is about 2,000 times bigger than the wavelength. So for light, in this case, for optical things we see, once you start getting about 1,000, we'll just round it to 1,000, let's say. We'll round it to 1,000. But this is kind of a soft. It doesn't go all of a sudden rays, quit working. Rays we must use wave theory. You can't just go ray to wave theory. It just, waves, the rays start working for bulk optics, the things we think like Newton stuff did, for mirrors and stuff. And then slowly you start seeing kind of a mixed effect. Mixed effects start showing up right about in here. And then you start seeing more just wave effects. So anything more smaller than this, you start seeing mainly wave effects. Now, we'll say that's 2,000. We can say 1,000 times bigger than wavelengths, just to make it an easy number. Rule of thumb, you could say. Now, it's interesting. 1 millimeter, half millimeter gaps we can see. Your paper's 1/10 of a millimeter thick or so, 0.6. Your hair, you could do this diffraction around a human hair. Hairs are anywhere from 550 micrometers or 0.05 millimeters to about 0.1 millimeter in width. So you could use diffraction with human hairs if you wanted. You could see that. Take 2 hairs and make, double slit diffraction there or something. You could take a razor, a knife edge, and scratch the back of a mirror and shine the light through it. You can see diffraction effects way out there. So this is something we can physically make. And you can see this wave phenomenon. Now, what I want to get is the bigger picture here is, this isn't just for light waves. This works for other waves. It would work for X-rays. With X-rays, the wavelength is so much shorter. You got to get really, really small gaps, like gaps between, say, crystals or atomic. So you've heard of X-ray crystallography, possibly. So they use X-rays to look at crystals because they're the only light that can get in there, and you get diffraction between those crystals, the atomic lattices. And the bigger size as well. Sound waves can show these effects. The wavelength of sound in certain rooms, you'll see interference effects. You can see diffraction with sound. You see radio waves here. Why do some spots maybe you get better radio signal than others? Well, if it's FM, that's got a wavelength of anywhere from a couple meters to 5 or 10 meters, let's say. There, maybe you have to be something metal, like metal fencing or metal structures, short in a building. If you have metal on your some of the supports, you can see diffraction there. Maybe you get places where it's really, say, FM radio in a building, you get a lot of signal and then no signal. Could be a diffraction effect. Radio waves, AM radio waves. AM radio waves can be, 200-300 meters long. So buildings themselves could actually show diffraction for AM radio, which is crazy. But it lets you see structures. That's pretty cool. If you think about how this is valid for just waves, anything, and in this case, electromagnetic waves, but you take any electromagnetic wave and use it for that. Now, that's pretty cool. That's pretty darn cool. I like this concept. Anything more than about 1,000, once you get about 1,000 times to the wavelength, you can start seeing diffraction, whether it's infrared. Infrared can be anywhere from like a micron to say 10 to 20 microns. You see microwave radiation, which can be say 100 microns or 0.1 millimeters, say a couple millimeters. You can see diffraction with microwaves. There used to be physics demos with that in labs and stuff. It's low-level microwave radiation. But why is that little grid thing in there that absorbs the microwave radiation on your microwave? Why can you see through it? Because the wave's so big, it's not going to be able to get through it. It's actually shorter than the width of that wave. If it's smaller, that wave, hardly any of it gets through. You're like, how can we see it and still stop it? What's diffraction effect? Diffraction is a very, very powerful effect. And understanding it and the sizes of things that cause it allows you to manipulate it and do things with it. Part of my job at Digital Optics involved that. It's some really, really cool stuff using diffraction. Holograms themselves are, as I said earlier, really fancy diffraction gratings. And where they manipulate these gaps, width and spacing of it, in X and Y, to show you a hologram or a picture that looks like it has depth in it. Okay? The wave nature of light, wave model. Once you're about 1,000 times bigger than that wavelength, that close, that much or smaller, when you're dealing with structures that size, got to use waves, you can't use rays. Next chapter, we're going to do rays. Not my Uncle Ray. We're talking about the Ray model of light. And I did have an Uncle Ray. Great Uncle. So, that'll be for next time. All right? It's chapter 33.